Hi everyone, my name is Suyash Agrawal and I am a junior undergraduate in Computer Science Department at IIT Delhi. This lecture is being recorded as a part of our COQ course and these slides are made jointly by me and Aman Agrawal, who is also a student of Computer Science Department. Today I'm going to talk about divide and conquer algorithms. So what are these divide and conquer algorithms? So you will see that divide and conquer is a pretty simple concept. It's just that you break the problem into smaller parts and solve those smaller parts in order to get a bigger solution. But you will see that this simple algorithm can be used to solve a large variety of problems, and you also use these concepts to solve some basic problems that you encounter in life. So during the course of this video lecture, we will explore various applications of divide and conquer algorithms so that you get an intuition of how this works. Specifically, we will look on first a searching algorithm and then two sorting algorithms. There are various other applications of divide and conquer, but we shall not be covering those because they require a much uh, bigger time to understand, and after seeing these applications you would be able to follow those if you read them from internet or some book. So in this lecture we are just going to focus on these three applications. So first up is binary search. So what do you mean by searching? So the problem statement is as follows: that you're given a sorted array of n elements and given a key, you have to find whether key k exists in the array or not. So this is a very formal kind of statement, so I will break it down for you. So we are given an array of elements, so we will have total of n elements and they are in a sorted manner. So what I mean by sorted is that they would have a property such that number at ith position is greater than or equal to number at I minus 1th position. So they are in increasing order kind of, or decreasing. It will also work on decreasing, but let's just focus on increasing order. And given a key k, so by key k I mean you're given a number, let's say 5. So you have to find whether 5 exists in the array or not. So the naive solution for this problem would be to just iterate through the array and check if the given key k exists or not. So you just start from the beginning of the array and check each element and whether that element is equal to the one you're searching for, and just return true or false if you encounter that element, otherwise false. So this is the naive solution. But did we use the fact that the array was sorted? So as we just iterating through the beginning of the array, we did not focus on whether the array was sorted or not, because the naive solution would anyway work on any kind of array. But here we are given the special property that the array was sorted. So is there some way in which we can use the given property that the elements are sorted? So take some time to think of how you would solve this problem. And let me tell you that you have already solved this problem. Like, you've already used this concept in your everyday life. So try to think about it. So pause this video and try to think about it. So let me tell you a situation in which in real life in where you use binary search. So I'm sure all of you have tried to look up a word in a dictionary. So let's say you're searching for a word camel in the dictionary. So how do you go about searching for a camel in a dictionary? So dictionary has a lot of pages, like thousands of pages, and each page has about like 50 or so words. So you don't go through the first element, like first word on the page, and go till the end until you find camel. So what you do is that you search for, and you like randomly open the dictionary and see any word, and as the elements in the dictionary are sorted, so you know that the letter starting from A will be before the word starting from letter B. So if you encounter a word G starting with J, you search in the beginning half of the dictionary. So this similar kind of concept is used in binary search, and you will see that this makes the searching very fast. So we will also analyze how fast this searching becomes in case of binary search. So now, so the basic algorithm is as follows. Take 2 pointers, set 1 to 0 and other to n minus 1. Actually, you know what, let's just skip this algorithm. We will come back to this algorithm, but let's first see how this algorithm works in visually. Then we will be able to better understand this algorithm. So let me just play this video and try to focus first on the sequential search, then on the binary search. So as you see, sequential search is just iterating through the elements in order to look for 37. So it would take a long time for it to search for 37 in the array. And also notice that these numbers are sorted, so they are in increasing order, like 3 is greater than 1, 5 is greater than 3, and so on. So the algorithm here, binary search, utilizes this structure in the problem. So it first looks at 23. So as 37 is greater than 23, it knows already that 37, if present, would be in this part of the array, and thus it saves the computation time to look at all of these elements in the array. So it first looks here, then here, then it would look here, and then it finds it. So it just finds whether 37 is in the array or not in just 3 steps, as compared to 11 steps that it would have taken for sequential search to look for 37, and that is quite a speed up. So now let us go back and look how to formulate this problem algorithmically. So we take 2 pointers and we set 1 pointer to the beginning of the array and other pointer to the end of the array, and then we look at the element that is between these pointers. So L at position L plus R by 2. Now if we find that the element at this position is greater than the elements that we want to look for, then we know that if the element T was present in the array, then it would be between position 0 and L plus R by 2. So we set the right pointer to m minus 1, where m is L plus R by 2. Else we know that if the element in the middle is less than the element we are trying to search, then it would be present in the right half of the array, and then we set L to m plus 1 and recursively search this. So now let us again look back to video and see how this algorithm was working there. So you see, first of all, it has set the left pointer to 0 and the right pointer to the last element, and it is looking at the middle element. Now as 23 was less than 37, it sets the left pointer to the next element, that is m plus 1. So it sets the left pointer to 9 and the right pointer is left unchanged. Now it again looks at middle element, so that would be now 41. So as 41 is greater than 37, it shifts the right pointer to 11, as you shall see now. Yes. So now it has set the right pointer to 11 and the low pointer was left unchanged. Now it will look at 31. So as 31 is less than 37, it sets the left pointer to 11 and right pointer is left unchanged. Now the middle would now be 11th element. So now as 37 is equal to 37, it just throws that the element exists in the array. Now if this was not 37, let's say it was 36, then it would have set the right pointer to be the left pointer to be 12 and the right pointer would have been 11, and then as right pointer is less than left pointer, so it throws out error, as you see here. So if L is greater than R, the search terminates as unsuccessful. So this would cover the case when element was not in the array. Now, having looked at the algorithm of binary search, we will try to analyze how fast is binary search as compared to sequential search. So, I will not give a very rigorous proof of the time complexity of binary search. You may look it up at Wikipedia if you want to, but just to give you an intuition, so let us first see how much time sequential search takes. So let's say we had an array of 1 million elements, and checking whether the current element is equal to the one we're searching for, let's say it takes 1 second. So in the worst case, in sequential search, we will have to look at all the elements in the array, and that would take 1 million seconds for us in the worst case. So the worst case time complexity of sequential search would be 1 million seconds, and that is quite a large number. So in case of binary search, how long would it take? So if you see carefully, what we're doing at every step in binary search is that we're halving the problem. So let's say at iteration 0 we had an array of n elements. So after first iteration, we reduce the feasible size of the array to n by 2. So we reduce the search space to n by 2 elements, because we have discarded the n by 2 elements that we are sure of that element would not exist there. So at every step we are halving the problem. So let's say at iteration 0 we had n elements, so at iteration 1 we would have n by 2 elements, next we would have n by 4 elements. So at ith iteration we would have n upon 2 to the power I 2 elements to search for, and thus our search would converge in log n steps. So log n, where log is base 2, not base 10. So how small is log n compared to n? So in 1 million situation, we would take log base 2 of 1 million steps, and if you calculate it, it turns out to be just 20, around 20. So our search would just conclude in 20 seconds whether the element was in the array or not, as compared to 1 million seconds that it would have taken in sequential search. And I am sure you would agree that 1 million seconds is very, very, very large than 20 seconds. So this is how powerful binary search turns out to be. And you will see that it's just not a special, like just a application of divide and conquer that we are using to teach. It's actually used in various instances in our life and in computer science in general, and this is a really powerful concept. So next up we were going to look at quicksort algorithm, which is a sorting algorithm. So now let us look at quicksort. So in quicksort we are again given an array of elements, and the problem statement is to sort these array of elements. So in binary search we were already given an array of sorted n elements. Now here we are given a random array of n elements and we have to sort it. So you can see it as a precursor of binary search. We first have to sort the array in order to binary search, and in order to sort the array we use a sorting algorithm. So here's a sorting algorithm named quicksort. So think about how you would go about doing it naively, like sorting naively. So how you go about is that maybe you would first try to find the minimum element in the array, then place it in the first place, then find second minimum, and then place it in the second place, and so on. So that algorithm also has a formal name. It's called insertion sort. So you could try to look up insertion sort if you want. But the quicksort here is a algorithm based on divide and conquer principle. So you will find that quicksort is quite fast algorithm as compared to insertion sort. So let us now look at how quicksort works. So the intuition behind quicksort is that it tries to divide the problem into smaller sub problems which are subsequently easier to solve, and by solving those sub problems we can combine those results somehow in order to get the solution of bigger problem. So how? So let us see that with a little animation first. So just a second. So yeah, you can see that it is doing something in order to break the problem into smaller parts. So like here it divided the array into two parts such that the first part is less than 3 and the second part is greater than 3. Now it would try to sort this part first, and then it would try to sort this part. So it may seem a bit complicated as of now, but let me tell you that it's quite simple once you understand how this works. So I'll be telling you how this is working. So let us first complete the animation. Yeah. Now as to the algorithm, so first we divide the array, like the intuition is to first divide the array into smaller sub-arrays and sort these sub-arrays in order to get a bigger sorted array. So the steps are, first pick a random element in the array. So we generally pick the first element or the middle element, but it's best to choose a random elements in the array. So pick the element and we call it pivot. Now we partition the array such that the elements before the pivot are less than the pivot and the elements after the pivot are greater than the pivot. So this partitioning is the key to how we divide the array, and we recursively do this to both the partitions. So now you may not be able to understand it fully now, so let us again go back to animation and see how this algorithm is working there. Now so here it first chooses a pivot, so the pivot is 3. Now it will try to partition the array such that all the elements before 3 are less than 3 and all the elements after 3 are greater than 3. So just see how intelligently it's going to partition the array. So now it has swapped 2 with 6, as 6 was greater than 3 and 2 was less than 3. So it swapped those so that 2 comes at a place which is before 3 and 6 comes after a place which is after the place of 3. Now it will swap 5 and 1. So now the end result is that we now have a smaller partition here which is less than 3 and a partition here is greater than 3. And you could try to think that if we sort this and if we sort this, then the array we would get would be sorted, fully sorted. So now after fixing 3 here, now we'll try to sort this partition of the array. So it selects 1 as a pivot and then it would swap these positions. Yeah. So now the left partition of the array is sorted. Now it randomly chose a pivot here, so it was, let's say, 4. So now it will partition this array into 2 smaller sub-arrays such that one is less than 4 and other is greater than 4. So yep, it finishes here and it sees that this whole part is greater than 4, and actually no part here was less than 4. That's why we do not see a partition here. Now let's say it choose 6. Now it will similarly divide the array such that the part on the left is less than 6, the part on right is greater than 6. Yeah. So now the part on the left part is less than 6 and the right part is greater than 6. To sort 5, as single element is already sorted, so it does not do any work here. Now it will sort this. This is already sorted, it does not have to do any work here. So as you see, now we have got a sorted array. So I hope that you got an intuition on how quicksort works in this case and why this algorithm is a part of divide and conquer, because we are basically partitioning the array into 2 smaller partitions and sorting them recursively. Now let me quickly tell you about the running time complexity of quicksort. So analyzing the time complexity of quicksort is not as easy as it was in the case of binary search. So like in the worst case it is order n squared. So hopefully you know about what order is. So quickly, just order means how much, like what, if you calculated the time, how the time would grow as the size of input grows. So order of n means that it would take linear time. So as you increase the size of the array, the time taken would increase linearly with the size of the array. So like let's say in array of size 10 it took 10 seconds, then in array of size 20 it would take approximately like 20 seconds. While if the complexity was n squared, then if the time it took in an array of let's say 10 elements was 100, then on size 20 it would take around 400 seconds. So that's a quadratic time complexity. So the quicksort algorithm in worst case may seem to take order n square time, but what we can prove is that in average case, so average is like you do a lot of iterations with various kinds of inputs and you take an average. So in average or amortized sense, quicksort just takes n log n time. So I will not be proving that here because it would take another video to prove how in amortized sense quicksort takes n log n time. But you can take my word on this and conclude that quicksort in amortized sense would take order n log n time to sort an array of n elements. Next up we are going to look at an algorithm named quicksort, and it is also a sorting algorithm, and you will see that it is also based on divide and conquer principle and is quite similar to quicksort as it's based on divide and conquer. So now for the merge sort algorithm. So here also the problem statement is same. Like we are given an array of n elements and problem is to sort these array of numbers. So you can also try to think of how to come up with a divide and conquer algorithm for this, which is different from quicksort. So the intuition in this case is to break the array into smaller subarrays without doing any work, and then sort these smaller arrays and then merge them. So let us again see how this works with a little animation. Yes, so it breaks the array into two parts first, then break them into four, then breaks them into 8, and sort these parts individually. And then it would merge these parts. And finally merge these parts to get the final sorted array. So don't be worried if you did not follow of any what happened. We will again come back to this after discussing the algorithm. So the brief overview of the merge sort algorithm is as follows. So we first split the array into two equal sized parts. So this is quite different from what we did in quicksort. So in quicksort we selected a partitioning element, and then we constructed two partitions with a special property that the left partition is less than the pivot and the right partition is greater than the pivot. But here we do no such things, and we simply break the array into two equal sized parts. Then we will recursively solve these two parts, like by solving I mean sorting these two parts. So we'll recursively sort these two parts, and after the recursive call ends we would have two equal sized arrays that are sorted. Now we will have to merge these two sorted arrays to get a bigger sorted array. So this merging part is also quite different from the one that was in quicksort. So in quicksort we did not have to merge because we constructed the arrays in such a way that concatenating them would just give us the sorted array. But here, as we did no special work while splitting the array, we now have to do some special work in order to merge these two arrays. So that's all the difference between quicksort and merge sort. And please take my word on it that this merging can be done in linear time. So we'll analyze the time complexity separately, but first let us again go back to the animation and look how it was working. So coming back to our animation, so as you can see that in the first step we just broke the array into two equal sized parts. Next we're going to further break these two parts into smaller parts. So and further we will again break these parts into still smaller parts. After this we've gotten all the arrays of single element size. So these arrays are automatically sorted. So single element array is anyway sorted array. Now then comes the merging part. So now we will merge these two parts in order to get the bigger parts. So we first merge these two parts in order to get a sorted array of size 2. Similarly for others. So here again we merge these two, we merge these two, and we merge these two. So at the end of this operation we've gotten from 8 single element sorted arrays to 4 double element sorted arrays. Now we will merge these 2 sorted arrays to get a 4 sorted array. So what I mean by k sorted array is that array of size k which is sorted. So now we take these two arrays and merge them to get a sorted array of size 4. Similarly here. So as you can see, after this operation we've got 2 arrays of size 4 which are sorted. So now we will merge these size 4 arrays to get an array of size 8 which is sorted. So yes, as you can see that after this operation we've got the original array back, except that this array is sorted. So hopefully you've got an intuition on how merge sort is working and how it is different from quicksort. So to repeat myself again, in merge sort we first break the array into 2 equal sized arrays, we sort them recursively and then we merge them. So merging takes only linear time, and the time complexity of this algorithm is again n log n, but it's also the worst case time complexity. So let's now go to complexity analysis. So for the time complexity, so if we work out, then we can write a recursion of form time taken for sorting an array of n elements is 2 into time taken to sort n by 2 elements array plus order n. So this order n is for merging those two arrays, which I asked you to believe me to be order n, and this is just a recursive call that we make. So after solving this recursion we will get that Tn is order n log n. So again I'm not going to solve this recursion in this video, so you can look up any of your discrete maths book to see how to solve these kind of recursions. But if you solve this recursion you will get that the time complexity in this case is n log n. So the difference here is that in quicksort the worst case time complexity was actually order n square, but in merge sort it would always take order n log n time. So it's in some sense slightly better algorithm than quicksort, as it is guaranteed to take at most n log n time to sort these two arrays. So there are some differences, like some trade-offs between merge sort and quicksort, but that is not the essence of divide and conquer, so we will not discuss that here, but you can look that up on Wikipedia or on internet to see the differences. But you see that how divide and conquer can be used to simplify these problems and get a better time complexity than was possible in ninth case. So concluding, we saw that divide and conquer is a very powerful technique, so it can be applied in a lot of domains, in a lot of problems of computer science, and almost always we get a speed up than what would have been a time complexity in case of naive solution. So in that sense, you should always try to look up a divide and conquer solution to an algorithm or a problem that you're facing. So divide and conquer is applicable when the structure of the problem allows breaking it into smaller sub-problems of similar type. So this was the case in binary search, quicksort, and merge sort too. And as I already said, it improves the time complexity of the problem as compared to naive algorithms. And popular use of divide and conquer algorithms can be seen in binary search, quicksort, merge sort, finding kth smallest element, finding closest pair of points. So we looked at binary search, quicksort, and merge sort in this video, and these two are slightly more complicated cases, but after looking at this, I'm quite sure that you would be able to follow how divide and conquer helps in these cases too. So do look it up on internet to understand how divide and conquer works in that case. And finally, thank you. So thank you for watching this video, and I hope that you got an intuition on how divide and conquer works and why is it a very powerful technique.